in 6-5. We're still dealing with matrices, of course. But today we're going to talk about something called determinants and then ultimately inverses. Okay, so every square matrix has a real number called a determinant. The determinant of matrix A is denoted as det of A, or we put A in these vertical lines that kind of look like absolute value. But inside the absolute value, there will be all the numbers of a matrix, so it's not really hard to confuse it with absolute value. Okay, the determinant of a 2 by 2 matrix is called a second order determinant. To find the determinant of a 2 by 2 matrix, use the rule. Okay, then this is how we would write determinant of it. I would just put those vertical bars around it instead of the square brackets. And then this is how I calculate it. Okay, when we read on a page, we start upper left, correct? Okay, so we're going to start upper left and multiply A times the number across from it, and then subtract the other cross product. Okay, you start upper left, multiply, subtract, multiply. Now, I want to jump back here for 1 second. Every square matrix has a determinant. What does square matrix mean? Yeah, 2 by 2, 3 by 3, 4 by 4, etc. So if it's a 1 by 4 or a 2 by 5 matrix, it just doesn't have a determinant. Okay, so this is how we find the determinants. Here's our matrix. So I'm going to start with the -4, top left, and I'm going to multiply the number across from it. And then I will subtract the product of the other two. So that's 40 minus 15 is 25 is the determinant of that matrix. Okay, now all we're doing right now is finding this determinant. On Wednesday, I'll show you what these determinants are used for. Remember, way back when I said 3 ways to solve a system of equations, but you're going to learn 2 more. One new method that we learn will use these determinants. So for today, we're just finding them. We'll actually use them for something on Wednesday. Okay, so for this next one, start upper left, multiply by the number across from it, subtract the product of the other two. So that's a positive 12 minus a negative 33, and minus the negative, of course, becomes plus positive. So that one gives me 45. Could I get negatives for these? Sure. Could I get a 0? Yeah. What if these two quantities were the same and I was subtracting them? So it's fine to get positive, negative, or zeros on these determinants. All right, you do number 3. I'm going to set mine up here, but I just won't talk through it. Check up here when you're done. So what's going to mess us up if we miss these? Negatives, parentheses, not remembering to subtract in the middle there. So be very careful with your subtraction and your negatives on these. All right, just for the heck of it, let's do the last one. Any issues with that one? Okay, so get your colors ready. That's how we do a 2 by 2 determinant. That's how we find a 2 by 2. Now I'm going to show you how to do a 3 by 3 determinant. So this is a matrix. We're going to find the value of the determinant. Since there is it's crowded above this in words, I'm going to come down here and repeat these numbers. but I'm going to leave a little row here to write some more numbers. Okay, so I'm going to come down here. I'm going to bring down 3, -5, 1. Don't bunch these together. Kind of space out your columns just a little bit. Because if you bunch them together, those negatives are going to get really messy. So leave enough space that you can clearly see each column. Okay, what I'm going to do next is repeat the first 2 columns so that I have a total of 5. So this was column 1, column 2, column 3. I'm going to repeat the first one and repeat the second one so that I have a total of 5 columns. Okay, take one of your colors. We're going to start upper left, and there will be a diagonal of 3 numbers. And we're going to multiply all those numbers on the diagonal. So that's 12 times -1 is -12. Okay, if they get too big for you or you're just afraid you're going to make a mistake, use your calculator. Then I have another 3 by 3 diagonal right next to it. So that's positive 35 times 1 is 35. And then I have a third diagonal of 3 in that same direction. So that's -10 times 5 is -50. Okay, get your second color. You don't have to use color. I just think it's prettier and it makes it easier to see the different numbers. Okay, I'm going to start bottom left and go the other direction 3 diagonals. Okay, so that's 8. The next one is -25 times 3, -75. And then you should have a third one, and that's 5 times -7, -35. Okay, so we had 3 diagonals in each direction to find the product of. Okay, so remember up here with the 2 by 2s, we took this product and subtracted the one in that direction. So what we're going to do is same direction start with, the ones that were going down to the right. I'm going to add those numbers up and subtract all the ones in the other direction. Okay, so you might want to use your calculator here. Let's see. That's going to be a -27 minus -102. And of course, when I subtract that negative, that's going to be positive. And I'll get 75 for my determinant. Questions on that? So no harder, just a little bit longer. Certainly more places to make a mistake with your negatives, so be super careful. Questions on that one? Well, let's do number 6. So I'm not going to rewrite this one because I have room up here to put those numbers. Now you can see why I didn't go from here, because I didn't have room to write those numbers up here. But with this one I do have room. So I'm just going to repeat first column and second column so that I have a total of 5 columns. I'm going to start upper left, and I should have 3 diagonals with 3 numbers in each one. Let's see, so that is 16 times 6. That will be a -96. That will be 18. And 36. other direction. Make sure we're getting the same numbers there. And then start with the direction that started from the upper left. Add all of those together. And then subtract the sum of those numbers on top there. And 14. Let's see if we get the same thing. Kind of fun? Anybody have a question? All right. Okay, so let's drop down here. Do you remember those cool area formulas that we used when we were doing sine and cosine and tangent? They were area of a triangle formulas. One of them had that big square root like S times S minus A times S minus B times S minus C. Does that ring a bell? Okay, well, here's another cool little shortcut for area of a triangle. If you know three ordered pairs, so if you're talking about a triangle on a graph, then we can find the area of the triangle using determinants. Very cool. Okay, so what we do is we take the three ordered pairs and list them. There's your first, second, third order pairs, and then the third column is all ones. And if you evaluate that determinant and then multiply it by 1/2 or divide it by 2, that's the area of the triangle. Now, can you imagine coming up with that, like realizing that that relationship existed? I can't imagine how smart you would have to be to just sort of discover that relationship. But thankfully someone did for us. So if we have three order pairs, we can use the determinant to find its area. So let's find the area of this one. The area will be 1/2, which I'm going to worry about in a little bit. The determinant, first order pair is -5, -2. Second one is 3, 9. Third one is 7, -4. Then that third column is all ones. Okay, so that's a 3 by 3. So I'm going to repeat the first two. And then do my diagonals, sum everything up, and then last step I'll take that 1/2 and either multiply by 1/2 or divide by 2. Okay, so these are some bigger numbers. You might want to use your calculator for these. Actually, they're not too bad, are they? Right. Check, make sure we got the same numbers. Okay, so I'm going to start with the ones that originated top left. Add them up. And subtract the sum of those in the other direction. getting negative 148. Okay, now remember I'm finding area of a triangle. Area of a triangle is not going to be negative, right? So if you get a negative, you just absolute value it, take it, make it positive, because we knew it represents area and it will be positive. Now, if I got a 0, that is a red flag, because I can't have 0 area in a triangle. But if you get a negative, just make it positive. So we do the 148 here, and I multiply it by 1/2, which is the same as dividing it by 2, and I get 74. I didn't have any units to, you can write square units if you want to, or just leave it 74. Cool? All right, so let's apply it to this little problem here. Wellspring is 14 miles north and 3 miles east of Chester. Hilford is 8 miles east and 5 miles north of Chester. Find the area of the landform between these two towns, or these 3 towns. I'm going to let one of the cities be at the origin. Which one should I use for the origin? Chester, because the other 2 are given in relation to Chester. So I'm just going to say, all right, Chester's located at 0, 0. Okay, where is Wellspring if it's 14 miles north and 3 miles east in terms of an ordered pair? 314. Does everybody see where we got that? Does everybody see why it's not 14.3? Because picture the origin. Remember, this is north, east, south, west. So if it is 14 miles north and 3 miles east, then we went up 14 and right 3. So that ordered pair would be 3, 14. Does that make sense? North 14, east 3. But when we write that ordered pair, we always put the x-coordinate first. Okay, Hilford is 8 miles east and 5 miles north. So that means I'm going over to 8, but up to 5 for that ordered pair. So it would be 8, 5. Okay, so now I have my 3 ordered pairs. I will make my determinant that will look like this. 0, 0, 3, 14, 8, 5. The third column is all ones. But I've got to repeat the first 2 again. 0, 3, 8, 0, 14, 5. So that I have a total of 5 of them. And now let's work our math magic. Ooh, zeros are good, because if zero's in a diagonal, what's the whole product? 0, yeah. So I love it when I see some zeros. Got a negative again, so we're just going to make it positive. And the area will be 1/2 times 97, which is 48.5. Now we did have units here. This was given in miles, so that will be square miles. We didn't have to find the base, we didn't have to find the height, we didn't have to know any angles. Kind of a cool little tool to know there. Questions? So let's talk about some real numbers just for a second. You don't have to write this down, but if you want to write it down, you certainly can. In the real number system, what is that number that I can multiply any number by to get that same number back? 1. Okay, that is actually called a multiplicative identity. So 1 is our multiplicative identity. 1 times negative 3/8 is negative 3/8. 1 times anything is that number. Okay, there is a matrix that works the same way. Okay, so if I had a 2 by 2 matrix, what could I multiply it by to get that same matrix back? Okay, so let's just take a simple matrix. Let's say I had 3, 2, 5, 1. There is a matrix, and this is only for square matrices again, so 2 by 2, 3 by 3, etc. There is a matrix that I can multiply that by to get the same matrix back again. So if I call this matrix A, and I get A right back, we call this the I matrix for identity. So it acts like a 1. Okay, I have never, ever, ever told a class what this is. They have always figured it out eventually. So you're going to figure it out. Throw some ideas out there. Let's test them. Okay, so all ones. Okay, so when we multiply, I go across and down. So 3 times 1 is 3, plus 2 times 1 is 2. So 3 plus 2 would be 5. Okay, that's a very good thing to start with, but it didn't work, so how can we tweak it? Times 1/2 where? Like all of them 1/2s? Okay. Try it. And this is how you figure stuff out. Like you get it wrong and then you realize, oh, well, let's try this. Well, let's try that until you finally get there. Okay, so I'm going to go across and down. So 3 times 1/2 is 3/2, plus 2 times 1/2 is 2/2. 3/2 plus 2/2 is 5 over 2. Okay, let's try all ones and all zeros. So top row 1, bottom row 0. Okay, across and down. 3 plus 0 is 3. Okay, let's see if top row, second column work. 3 plus 0 is 3. Okay, I'm hearing about 4 different things, I think. Okay, what were you going to suggest first? Switch those? Someone else said that too. Okay, so let's try that. Okay, 3 plus 0 is 3. Let's do top row, second column. 0 plus 2 is 2. Second row, first column. 5 plus 0 is 5. 0 plus 1 is 1. That's it. See, it didn't take long. All right, but we got there by trying wrong things first. So the streak continues. I've still never told a class what it is. You discovered it. Yes? Because when we multiply, we go across and down and pair them up. So that would be 3 times 1 plus 2 times 0. I did. I was just doing the multiplication in my head. Yes. Okay. We're good? Okay, so let's fill that in on our notes then. The identity matrix denoted I is a square matrix that when multiplied by another matrix equals the same matrix. If A is an n by n matrix and I is an n by n identity matrix, then A times I is A and I times A is A. So I can take that identity matrix and multiply it on either side, and I should get the same one right back. So you guys just discovered this is our 2 by 2 identity matrix. If it's a 3 by 3, it looks very similar. Do you see the pattern? You have 1 in the diagonal and a 0 everywhere else. So if it was a 5 by 5, it would have 1 in that diagonal, 0 everywhere else. Okay? All right. 2 n by n matrices are inverses of each other if and only if their product, which means multiply, right, in both orders equals I. Okay. If matrix A has an inverse denoted as A inverse, then A inverse times A is I, and A times A inverse is I. Okay, so let me take a little break here and talk about real numbers again. Okay, in real numbers, I is this identity, which is 1, right, the equivalent of 1. I can multiply 5 times 1/5 and get 1. I can multiply negative 3/8 times negative 8/3 and get 1. What do we call these numbers to each other? What kind of inverses? We have additive inverse and multiplicative inverse. Multiplicative. So these are multiplicative inverses. That's a really fancy word, isn't it? Or term. Okay. Not multiple, multiplicative. Sorry about that. Okay, there is a simpler word that we use for those, and it starts with R. Reciprocals. Okay, so when we talk about reciprocals, they are actually multiplicative inverses. When we multiply those together, we get that identity 1. So this property exists for matrices also, and that's what we're talking about here. So basically this is saying if a matrix has an inverse and you multiply them, you get that 1 matrix, which is this. Now, I'm not going to have you discover what that is because we might be here all day and still never get it because it's kind of a really weird rule that we'll look at on the next page. But for this example, all we're going to do is see if they are inverses. So what I want to know is, if I multiply them in either order, will I get I? And I is 1, 0, 0, 1. So all we're going to do is multiply them. Okay, so let's find A times B. Let's just leave them in the order that they're in and do the multiplication. So that would be negative 1 times 5 plus 2 times 3. First row, first column. Okay, first row, second column will be negative 1 times 2 plus 2 times 1. Second row, first column. 3 times 5 plus negative 5 times 3. Second row, second column. 3 times 2 plus negative 5 times 1. Okay, so let's see what we get here. Negative 5 plus 6 is 1. Negative 2 plus 2 is 0. So far, so good. 15 minus 15 is 0. 6 minus 5 is 1. So if I get that identity matrix 1, 0, 0, 1, then yes, they are inverses. And we could switch the order. We could find B times A, and if they're inverses, we'll get the same thing. Question? All right, let's try number 2. I won't talk through this one, so let's do 2 and see if they are inverses with each other. the same thing when you're done. Okay, so when you got that first number, did you kind of already know it wasn't going to work out? I would keep going, because what if this was the only one that was wrong and these were what they should be? Then that would give me pause and make me think maybe I made a mistake. So I would still go ahead and finish out all four. But clearly that didn't work, did it? So these are not inverses. All right, so they're not kind of like that, what we would call a reciprocal in real numbers. Oh, should we do the fraction one?
No.
Oh, we love fractions.
No.
We are not afraid of them. No, we're not. Oh, let's do it together. Here we go. -3 times -1/4 plus -2 times -1/8. -3 times -1/16 plus -2 times 3/32. Just your average little fractions. So harmless. Okay, second row, first column. -4 times -1/4 plus 8 times -1/8. Last row, last column. Okay. Now, if you need your calculator, get your calculator. I'm going to be brave and not use it. 3/4 plus 2/8, which is 1/4. 3/16 minus 6/32. 4/16. Oops, nope, I messed up there. 4/4 plus -8/8. 4/16 plus 24/32. Whew! All right, Lily. What's 3/4 plus 1/4? 1. It's 4/4, which is 1. Okay, that's a good sign. Maybe they are inverses. What's 3/16 minus 6/32? 0. 4/4 is 1. -8/8 is -1. Add those together, we get a nice big 0. And believe it or not, those added together will be 1. So yes, those were inverses. So again, Wednesday, can't remember which day, we're going to use inverses to find yet another method to solve systems of equations. But for today, we're just finding the inverses. Okay, not all matrices have inverses. First of all, it has to be a square matrix. And secondly, not even all square matrices have inverses. Matrix A does not have an inverse if its determinant equals 0. If the determinant is 0, it will not have an inverse. And I'll show you why here. Okay, the very first thing that we do when we find the inverse is we find the determinant. So we find the determinant, A times D minus B times C, and we put 1 over that number. So if I got a 0 and I put 1 over 0, what is 1 over 0? Undefined. Then I can't find an inverse. Okay, so if your determinant is 0, you will run into a brick wall because you can't put 1 over 0. Okay, but if it exists, we put 1 over the determinant. Look at these two matrices. How are they different? What did I do to the first one to get the second one? Switched A and D. and negated B and C. See, A and D totally switched places, and then I put a negative in front of C and B, which means I negate it. If it's positive, I make it negative. If it was already negative, I will make it positive. Okay, so this is how we find the inverse. First thing, find the determinant. 4 times 3 minus negative 6 times negative 1. That's 12 minus 6 is 6. Okay, I didn't get 0, so we have an inverse. Okay, so the inverse will be 1 over 6 times, now we do the little switcheroo thing. A and D switch places. 3 and 4 switch places. These other two numbers here, I'm going to negate them. If this is already a negative, it becomes positive, and same for that one. Switch those two places, negate the other two. Now, this is scalar multiplication. So basically this says, take everything in this matrix and multiply it by 1/6. So my inverse will be 3/6. They're like out of control today, aren't they? 1/6, 6/6, 4/6. And then I can simplify that. So A inverse will be 1/2, 1/6, 1 and 2/3. And that's how I find the inverse. So if I were to multiply the original and this one, what would I get? 1, 0, 0, 1. Okay? All right, let's do 2 more, and then I'll get the homework to you. Okay, let's jump to number 5. Okay, first step is to find the determinant. 8 times negative 1 subtract 2 times negative 4. Negative 8 minus negative 8 becomes plus positive 0. When we get a 0, we can't put 1 over 0, so this does not have an inverse, so it is not possible to find the inverse. And we're done. Okay, number 6. Last one. Oh no, I wrote through that number. Find the determinant. 8 times 5 minus 8 times negative 10. 40 minus negative 80 becomes plus positive, so I get 120. It does have an inverse, and that inverse will be 1 over 120 times, switch the 8 and the 5, switch their location, then negate the other two, so the 10 becomes positive, the 8 becomes negative. And now that just means scalar multiplication, so everything inside this matrix gets multiplied by 1 over 120. Well, let's just use our calculator for that one. 5 over 120 becomes 1 over 24. Negative 8 over 120, negative 115. So 1/12. 8 over 120, 115. And that's our inverse. Question? Alrighty. Notice on the agenda we are going to do a quiz tomorrow over the stuff we've done with matrices here, like the multiplying and these inverses and the determinants. But of course we'll go over the homework and take any questions before the quiz.